And we're back. So, we left off talking about gravity, and we had figured out that the acceleration due to gravity, or the gravitational field strength, is equal to capital G, the constant, the mass of whatever planet you're dealing with, and the radius of the planet squared. And that gave us 9.81 as an average value for the Earth. But the first correction we need to talk about is the fact that the Earth is not spherical. The Earth actually bulges at the equator a little bit due to the fact that it's liquid and rotating. So it is an oblate spheroid. So the first correction, oblate spheroid. That means that it has an average radius of 6.37 times 10 to the 6 meters. But the polar radius is actually 6.357 times 10 to the 6 meters, a little less. And the equatorial radius is 6.378 times 10 to the 6 meters. So if you put in the polar amount, polar, then what you're going to get is 9.8. Well, it looks like a 5 goes here, meters per second squared. So much stronger attraction due to gravity. Well, it's got a 5 in the third decimal place when you're at the poles, because you're a little closer to the center of the Earth. And the equatorial number is 9.78. So if you want to lose weight, you could just go stand on the equator. There you go. Another problem with G is that the Earth is spinning. And the spinning Earth creates an issue, because if you're standing on the equator, you're going around. Here's an axis. You're going around this way. And so actually some of the gravity needs to be used to be your centripetal force, and the remaining part will be the normal force on you. In fact, if you're standing on a scale, we could draw a free body diagram for you that says, hey, here's going to be your mg force, and this is going to be the normal force, but the centripetal force needs to be provided by mg minus the normal. So your effective weight is going to be mg minus fc, the centripetal force. Now, in terms of what am I saying here? In terms of rotational speed, omega, the centripetal force winds up being omega squared times r. That's what happens when you replace the v with omega times r. And in the v squared over r, you get this. So if you were to actually do this, you would have your mass times 9.78, because that's the equatorial acceleration due to gravity, minus, now this is the tough part. We worked this out in a homework problem, and I looked it up, 7.27 times 10 to the minus 5, quantity squared, and then that equatorial radius, 6.378 times 10 to the 6. Okay, when all is said and done, that's going to be 9.78 minus 0.03 for a grand total of 9.75 meters per second squared is your apparent acceleration due to gravity, because of the Earth is spinning and it's an oblate spheroid. So those are some corrections, and that gives you an idea of the range of the acceleration due to gravity. There's some more things you can do. Obviously, if you were to go to the top of the tallest mountain on the Earth, you would be a little further away, and that would drop your acceleration due to gravity a little more. What if you started digging into the Earth? And we're going to see what happens when you dig into the Earth in just a moment. So let's see, get a piece of paper out here. Boom, boom, boom. So next item of business is to deal with the shell theorem. And part of the delay in publishing Newton's Principia, which included his theory of gravitation, was in proving something in calculus called the shell theorem. And the shell theorem says that a uniform shell of matter attracts a particle that is outside that shell as if all of the shell's mass is concentrated at its center. So if we have a spherical shell of material, and I'm just going to draw a sphere, and you had a particle over here, this entire sphere acts as if its mass was concentrated at its center. And so you could build up the Earth out of shells, first very small, then bigger, 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 until you get to the outside edge of the Earth. As long as you're far away from the Earth or outside of the Earth, it'll be as if the entire Earth's mass is concentrated at its center. That's not a surprising result because that's kind of like our definition of the center of mass. But a uniform shell of matter doesn't attract a particle that is inside of the shell. That means that if our particle is inside of this hollow shell of material, there is no force whatsoever. What that means is that as you dig into the Earth, and let me just draw a curvature of the Earth here. I'll go a little further. As you dig into the Earth, only the remaining radius of the Earth towards its center is important to figuring out how much material attracts you. So if you're standing at the bottom of this deep hole, this stuff above you, this stuff does not attract you at all. Because for every bit that's above you pulling up, there's a bit on the other side of the Earth pulling down, and it all works out to average out to zero. Only the stuff interior to your location. So that means that only the Earth, this is if you're standing on a smaller planet now. Also, that means that if you were to hollow out the Earth, you could float around inside a hollow Earth with equal amounts of material on all sides of you. That'd be kind of fun. There was a moment in the Hitchhiker's Guide to the Galaxy books where they went to visit a planet and they went into a cave and popped out inside the planet in a hollow space inside the planet where they were building other planets because this was a factory for planet building. There was an extra bit to this where the space inside the planet was bigger than the planet itself, so there was some sort of magic going on there. But the idea of using the inside of a planet as a place where you could, construct things is a true, scientifically true idea. Okay, so this is the shell theory. Now we have to figure out the upshot of the shell theory and figure out what the gravitational attraction looks like as you go inside the Earth. So this is going to be a little bit daunting here, and I've got two black pens, and one of them is smashed, and I don't know which one it is. So again, with this picture of the Earth, and let's draw the whole Earth. And now we have started to dig a hole, so there is this much of the Earth still inside of our location. So we are, a distance, well, this is the distance, r inside. So force of attraction is going to be capital G, little m, capital M, mass of the Earth, mass of the particle or person, divided by r squared. And so for this application, it's going to be the mass inside our location, because that's not all of the Earth's mass, and the radius inside our location squared. So how are we going to figure out how much mass is inside of our location given how far we've dug down and what's remaining of the Earth? We're going to use the density concept. The density concept says that there is this thing called density, which in physics is abbreviated with the Greek letter rho, and it is defined as the total mass of the Earth divided by the volume of the Earth. And of course, the Earth is a sphere, and we're assuming a uniform sphere. So that's going to be the total mass of the Earth divided by 4/3 pi times the radius of the Earth cubed. That is a constant number. And so calculated from the entire mass of the Earth and the entire radius of the Earth, you get a constant number. But we can also exploit the concept of density by saying that this is also equal to the mass inside of our location divided by 4/3 pi times the radius inside of our location cubed. You see, if it works for the entire Earth, it also works for any fraction of the Earth. And this is how we're going to find out what the mass inside is. We're going to claim that the mass inside of our location is going to be, now we're going to take this stuff on the bottom and multiply on the top. The 4/3 pi's are going to cancel. So we have the mass of the Earth, the entire mass of the Earth, and then we're going to have the radius inside cubed divided by the radius of the Earth cubed. Putting that into the thing here, we're going to wind up going back to, I believe this is the right pen. We're going to put it back inside this formula up here, and we're going to get that the force as you're digging inside the Earth is capital G, capital M. The mass inside is now going to be the mass of the Earth, and then we're going to have radius inside cubed, and then on the bottom we're going to have radius of the Earth cubed and radius inside squared, meaning that this is a constant times how much radius is still inside of our location. So if we were to graph this, how much gravitational attraction you would have as a function of radius, and here is where the outside of the Earth is. This is the radius of the Earth. If you're at the core of the Earth, you got 0. Then you have a linear increase until you get right over here, and you pop outside the Earth, and then you get 1 over r squared, and this is linear increase. So as you get closer and closer to the Earth in your spaceship, you feel a stronger and stronger attraction until you go through the surface of the Earth, and then the attraction drops off in a linear fashion because this cube cancels this squared, and you wind up with that. All right, so that's a little thing about tunneling into the Earth. There have been some very interesting things done. So a discussion of it's not practical, but what if you were to make a tunnel through the Earth in order to get from some place like, let's say, Europe to Australia very, very quickly, or America to Australia? It doesn't have to be through the center either. This works no matter whether you go through as a chord, like, skimming through part of the Earth, or whether you go straight through the core. If you were to drop a vehicle in one end, it would be attracted towards the center of the Earth, but in a decreasing fashion, and then by the time it got to the center, it would be going its fastest, but the attraction would then drop to 0, and as we came out the other side, the attraction would increase again, going the other way, and would slow down the vehicle, and it would pop out the other side with 0 velocity. And the trip would take, I believe, 18 minutes, no matter whether you went through a chord or through the core of the Earth. Now, you'd have to, first of all, dig this tunnel through a molten Earth. This is not practical. And then you'd have to suck all the air out of there, so there was no air resistance to this journey. But you could just drop people, and in 18 minutes, if there's a tunnel from one place to the other, using gravitation alone, you would get there. Now, what's interesting about this is the gravitational acceleration would start at 1g, and then drop to 0 and then go back to 1g. So it's not uncomfortable for people to take this trip. So if there was a solid planet out there and we wanted to come up with a planetary subway system, we could use this gravitational thing here. It's kind of a cool deal. All right, now there's a couple more things I want to do before we talk about gravitational potential energy, and I think I'm going to save gravitational potential energy for another day. But we need to talk about spaghettification. And we haven't used the green pen today, so let's rock on that one. Okay, so this is spaghettification. Hopefully I can spell this right. And spaghettification is a gravitational phenomenon where if you approach something that's like a black hole, you wind up with a problem, a structural problem. That's what people talk about. Hey, let's go through the black hole and see where it comes out. Maybe a black hole here is a white hole somewhere else with material spewing out of it, and that creates a wormhole, and we'd be in another part of the universe in no time. Well, you're not going to make the journey. Here's why. As you approach the black hole, and I'll just write BH for black hole here, as you get close, let's just say that you're going to dive in with just your body, but this would work for a spaceship as well. Here's you, and your head is closer than your feet are. And because gravitation depends on the distance squared, that small difference in distance as you get close creates a differential force that rips you apart and tries to stretch you. So a spacecraft of even 20 meters long would have its nose torn off of its tail as you approach the black hole. But there's an even bigger problem, and that is that as you approach the black hole, the right side of your body is pulled a little to the left, and the left side of your body is pulled a little to the right, so you are crushed with a small amount, well, as it becomes larger as you get closer, a large amount of force that is pushing you. So you get turned into spaghetti. You get stretched the long way and crushed the sideways way, and you can't go through a black hole without being spaghettified. So fun, speculative space gravitational stuff, and I still recommend that you watch The Expanse if you're into space dramas and stuff. They get a lot of the science of space travel right, using rocket engines and subjecting yourself to large accelerations when you turn or speed up or slow down. Or you could just read about you could read the books. That's another thing. Anyway, just recommending that for accuracy. Okay, that's probably enough for today. We will tackle gravitational potential energy in our next video. So I'm going to publish this as AP Grav number 2. Enjoy.